Okay, this is question number 4. A Francis turbine is required to give 180 kilowatt output power under a head of 20 meter. Overall efficiency is 80% and hydraulic efficiency is 85%. The turbine speed is 600 RPM. Flow velocity is constant at Vf equals 0.3 square root 2 GH, and peripheral velocity at inlet is U1 is equal to 0.8 square root 2 GH. There is no whirl at discharge. So here the V whirl 2 is equal to 0. So determine the diameter of the runner at inlet, the Guidevane angle, the runner blade angle at inlet, the width of the runner at inlet, assuming blade thickness occupy 15% of the circumference. Okay, so from the question, we could draw our velocity triangle like this one. So we list all the parameter from the question. So I think you know this one, and then this is the equation for overall efficiency. We have the equation for hydraulic efficiency. So this is the equation given in the question. So and then this is the Euler head. So the diameter of the inlet. So we could use the U equal pi dn over 60. So we rearrange the equation. We could calculate the D. The diameter is U1 times 60 over pi n. So we substitute the value of U1 here. So to get the value of U1 here, so we just substitute with the equation. So because we don't have any information about the losses inside the pipe, so we assume that the height of these 20 meters is actually the effective head. So we use the 20 meters here, the effective head. So the U1 is 15.84. We substitute into this equation, so we will get the diameter is 0.504 meters. So and then the guide vane, you know, the guide vane is the vane here to make sure that the water will flow at certain angle. So we take this angle and then we could calculate it by using this correlation. So we could calculate the value of VF1 by using this one. Again, we take 20 meters as the effective head. So and then to get the V1 here, okay, we could use the equation of hydraulic efficiency. So we substitute everything again. The effective head here is 20 meters. So and then we get V1 is 10.53. And finally, we could use all of that, okay, to calculate the value of tangent theta here. So and then the runner blade angle at inlet. So runner blade angle, so it is about the VR here. So we take this angle, so we could have correlation like this one. We substitute the value, and then we could get it is 48.2 degree. So here, if you see like this one, we will find that U1 is actually bigger than V1. If you see the value here, so V1 is 10.53, but the U1 here is 15. So if you see the value here, you will find that U1 must be larger, longer compared to V1. So means that our velocity triangle here is wrong. So what you need to do is you need to change your velocity triangle instead of backward blade here with the forward blade. So with the forward blade, the inlet here, so you have the inlet, so you have the VR here, you have the U2 here, and then you have VF, and you will have V1 here. So you need to change the velocity triangle, and then you could calculate the value of beta here is actually at this one, at this area. So it's become VF. Okay, VF here, this is the height, divide by this length, which is the U1 minus V1. So we substitute the value, so we get it is 48.2 degree. So the width of the runner at inlet, assuming blade thickness occupied 15% of the circumference. So this is actually telling us about the value of K. So means that the value of K is 0.85. Okay. So and then we could calculate by using this equation. Okay, so we rearrange the equation. So we get the B1 here as this one. So we could substitute all the value. We get it is 0.143 meters. So we could calculate the value of Q by manipulating value from the overall efficiency. So we could get it is 1.147 meter cube per second.